Hello, everyone, and welcome. Thank you for joining us for the session on life cycle assessment of concrete buildings. As you get started, a few reminders before we get do not use the chat box to ask any questions for today's panelists. Instead, use the Q&A. With the Q&A feature, attendees can like a question to move it to the top of the list. And as always, the webinar content and additional resources will be available shortly after the session. Today's session, focused on the environmental impact of a building, is brought to you by National Ready Mix Concrete Association. This session qualifies for one AIA HSW learning units for those watching live. AIA with those units for you once you have finished the session. Today, you'll be hearing from Don Davies, who is the president of MKA, Stacy Olson, a global design resilience leader of Gensler's Wellness Practice, Katie Poss, the Director of Sustainability Initiatives for the National Ready Mix Concrete Association, and Brandon Ray, who is the Director of Building Innovations for the National Ready Mix Concrete Association. Thank you all for being here today. Brandon, I'll hand it over to you now.
I think I'm actually going to kick it off. Thank you so much, Rebecca. Let me share my screen here. And we will get started. Okay. Well, thank you all so much for being here today. Thank you for having us to speak. Rebecca already went over the learning objectives, so I'll skip over this and we'll jump right in. So I just want to start with a little bit of background and history on the NRMCA and our journey towards carbon neutrality. If you're not aware, the NRMCA is the industry-supported trade association for ready-mix concrete producers, and we represent roughly 70% of the concrete volume that's poured in the United States on an annual basis. We started our journey towards carbon neutrality back in 2009 by adopting a carbon reduction goal of 30% by 2030. But we soon realized that that wasn't going to be enough based on feedback from the design build community. So we subsequently committed to more aggressive carbon reduction goals in 2012 by adopting the Architecture 2030 Challenge for Products, which states a goal of 50% carbon footprint reduction by 2030 and carbon neutrality by 2050. They urged product manufacturers to use life cycle assessment and environmental product declarations, or EPDs, as the methodology for measuring progress. We launched our EPD program in 2014, and we published benchmarks for carbon footprint in 2014, in 2017, and also in 2021, just last year. And we actually demonstrated a 21% decrease in carbon footprint in 2021 compared to the 2014 values. We're very proud of this progress, but we realize we have a long way to go towards ultimately achieving zero by 2050. In 2016, we launched the Build with Strength initiative to reach out to the design build community to communicate, advocate, educate, and promote on concrete sustainability through transparency, innovation, and accurate measurement in support of our carbon reduction goals. And then last year, we reaffirmed our commitment by joining the Portland Cement Association and developing a 2050 roadmap to carbon neutrality. So I know many of you have probably seen this chart on the left here, but I just want to make sure we're all starting with an accurate awareness of our industry's impact on the planet and on contributions to climate change. So the built environment emits roughly 40% of global greenhouse gas emissions on an annual basis. About 28% plus or minus is due to operating buildings, heating, cooling, and powering our buildings. But about 11% of that is responsible is from manufacturing materials and from the construction process itself. Now, the Architecture 2030 Challenge states on its website that getting a handle on embodied carbon now will help the United States hit the net zero emissions goals of the Paris Climate Accord by 2050 and ultimately aid in moving the world towards a better climate future. However, in conjunction with addressing climate change, new construction is on the rise. We are building more buildings, we are using more materials. So that means that these assessment tools to measure embodied carbon and environmental impacts are more important than ever. Now, there are three materials, concrete, steel, and aluminum, that are responsible for 23% of total global emissions, mostly used in the built environment. I want to point out that that 23% value also accounts for use of these materials by other industries. This is where we should be focusing our energy. This is where we can get the most bang for our buck and have the biggest impact. Now, this chart on the right emphasizes embodied carbon impacts versus operational carbon impacts based on a 30-year time span. Some of you may have heard of the term time value of carbon. Unlike operational emissions, which can be reduced over time, say through building energy upgrades and hopefully a cleaner grid and increased use of renewables, these embodied carbon emissions are locked into place as soon as a building is built. Now, for this reason, predicting emissions and reducing carbon impacts from the beginning of a building project is absolutely essential. So what is life cycle assessment? LCA is the investigation and evaluation of the environmental impacts of a product, process, or service. LCA evaluates all stages of a product's life and considers the interdependence on each stage. It also allows a practitioner to make informed, responsible, and balanced decisions to deliver a product with optimized environmental performance. Now, there are several inputs, life cycle stages, and outputs associated with LCA. Inputs include raw materials and energy. Life cycle stages include raw material acquisition, manufacturing, use, reuse, and maintenance, and end of life, including recycling and waste management. The output of an LCA can be thought of as a wide-ranging environmental footprint of a building. These include emissions, waterborne waste, solid waste, co-products, and other releases. These outputs are then converted to potential environmental impacts based on scientific knowledge of how these outputs affect the planet, affect our ecosystems, and human health. Now, this boundary system can be applied to any product. It could be a piece of paper, a carpet, a cubic yard of concrete, a car, or even an entire building. One environmental impact tool developed by the US EPA is called the Tool for the Reduction and Assessment of Chemical and Other Environmental Impacts, otherwise known as TRACY. TRACY allows the examination of impacts associated with the raw material usage and energy consumption, or inputs, and chemical releases, or outputs, resulting from the process involved in producing a product, or in this case, the construction and operation of a building over a specific time frame. Ultimately, the purpose of TRACY is to allow a determination of priorities or a comparison of two or more options on the basis of environmental impact categories. Now, you may have seen some of these impact categories on an EPD. These are things like ozone depletion, acidification, eutrophication, photochemical smog, human health issues, ecotoxicity, fossil fuel use, land use, water use. And finally, the one that's receiving the most attention right now and the one that's most commonly quantified is global warming potential, or GWP. Now, these are the stages of the building life cycle. Whole building life cycle assessment allows us to model and estimate emissions associated with each of these stages. Now, holistically, the term embodied carbon technically includes all of these stages except for B6 and B7, operational energy and water use. Embodied carbon describes all stages of the material life cycle, not just A1 through A3. However, these product stage emissions are commonly evaluated today due to many reasons, one of which being that they can be quantified with the highest level of certainty. However, the practice of whole building LCA allows for evaluation of stages beyond the product and construction stages. You can find whole building LCA cited in various green building code standards and rating systems. Now, to conduct a comprehensive whole building LCA, one will need life cycle data for all of the significant building materials and products, along with operational data for the building, including energy use, water use, and waste production. Most of these green building schemes limit LCAs to measure only the embodied environmental impacts of building products. Mostly structural materials, sometimes enclosure materials are included, as these have the most significant embodied carbon profile. Now, green building schemes typically require an LCA comparison between two building designs, a reference or a baseline building and a proposed building. Success is measured through conducting whole building LCA and then demonstrating impact reductions. Now, there are various tools on the market that assist with project goals for reducing building life cycle impacts. From a whole building LCA perspective, the most commonly used are Athena's Impact Estimator, which is a free tool, One-Click LCA, and Tally. And these tools can measure all of the stages of the building life cycle that I showed earlier. However, there are other tools out there, such as the Embodied Carbon and Construction Calculator, that's primarily used in the procurement stage. And that tool only measures those A1 through A3 product stage emissions. And finally, there are some free tools out there that are specific to certain materials like concrete, such as the Slag Cement Association's Life Cycle Assessment Calculator. With that, I'll hand it over to Brandon. Thank you.
Thank you, Katie. Steal the screen here. And to pick up where Katie left off, moving into environmental product declarations, just a brief deeper dive. The mechanics of disclosing a product's carbon footprint and the ability to optimize comes from quantifiable, verifiable metrics called environmental product declarations. So EPDs. EPDs are essentially a focused LCA that look at the cradle to gate aspects of the processes to generate a product. So once generated, an EPD is effectively an attrition label for the individual mix design or product. In a structure, each mix has a specific function and performs as an individual specific product. The ready mix industry itself has alone around 35,000 product specific EPDs, which is actually probably higher than that by now because there are more created every day. As Katie touched on earlier, one of the key criteria on here is going to be the global warming potential, but there are other environmental impacts that are quantified via these documents. It is important to note, though, that EPDs cannot be used to directly compare the impacts of different materials, as the product category rules that govern EPD creation can vary and will vary between different materials. Additionally, since this is cradle to gate, the benefits of concrete's carbon uptake and recyclability are not going to be captured. So those benefits would be found in a larger scope whole building LCA, where the use and end of life stages are separately captured. EPDs themselves can be broken down into two primary categories for our purposes, product specific and industry wide. On the screen here, you see a product specific EPD, which is an explicit EPD for a specific mix design from a specific producer and a specific production facility. Many companies ultimately do have published EPDs for their concrete mixes, and most would be willing to publish them specifically for a project when asked. In the absence of a product-specific EPD, we can easily use NRMCA's industry-wide EPD, which is found here on the screen and downloadable at our website here, as you can see. In early design, where specific producers are not available, or at the decision table, I should say, the use of the industry-wide EPD is necessary, since official submittals with product-specific EPDs can be found or won't be on the project until months, if not years in the future. So the industry-wide EPD will help benefit the project team in terms of quantifying impacts upfront in the early stages of design. The industry-wide EPD is broken down regionally and can be very meaningful and accurate, especially when cementitious makeup and end use is appropriately accounted for. So how can concrete help reduce life cycle impacts? First, on the embodied side, concrete is largely a local material. You have water, sand, aggregate, and other ingredients that make up about 85 to 90% of a concrete mixture by weight. The process to manufacture, procure, and combine these materials in a concrete plant, and then ultimately transport them to a construction site is not an efficient, or is inefficient and not a significant contributor to greenhouse gas emissions. The amount of embodied carbon in concrete is primarily a function of the cement content. in the mix. And so therefore, one of the most effective and immediate ways to reduce embodied impacts of concrete is to increase the use of industrial waste products, or byproducts, I should say, to replace a portion of the cement used in concrete. With cement being the most expensive and carbon-intensive ingredient, its replacement is cost-effective and sustainable. Some of these waste materials can include fly ash from coal plants, both currently running and also historically landfilled. I hear that a lot, that fly ash supplies are going to dwindle because of turning off of coal plants, but there is a significant portion that is landfilled throughout America that we can access and are actively accessing and planning for incorporation into concrete. Slag from steel production is another byproduct that can be incorporated, and also silica fume. Overall, the cement producers within the country are also leading the way in regards to creating blended cements, which incorporate some of these materials directly in order to achieve the same benefit without having to add a separate ingredient. Additionally, there are such things as biochar, which is a form of burned waste from the wood industry that can be incorporated into concrete as an additive as well, to realize similar benefits. All of these, when put into use in the concrete, will improve the strength and durability of the material while reducing the embodied carbon. Typically, reductions are 20% to 50%, but it is not uncommon to see reductions of up to 70% in select mixes for certain applications. Next up is operational and use stage benefits of concrete structures, which include the positive impacts of thermal mass on energy demands, both in magnitude and timing. Additionally, the resilient and durable nature of concrete will reduce maintenance needs while increasing the reliable longevity of the building. And lastly, end of life, which benefits include carbon uptake, where concrete will actively absorb and permanently sequester CO2 from the atmosphere throughout its lifespan. This is a phenomenon that does occur in the use stage as well, but I'm just listing it here in end of life for simplicity. Additionally, concrete is fully recyclable when crushed and can be reused in new concrete mixtures as an aggregate or as a base rock material for various other applications. Apologies on that. And then moving forward, some of these aforementioned benefits are a bit intricate, and I encourage you all to see our recent presentation to AIA California, the top 10 ways to reduce concrete's carbon footprint. This can be found on AIA's California's website on the link there on the screen. Beyond concrete's inherent properties that can benefit a structure's operational energy efficiencies, there are ways in which its embodied carbon can easily and significantly be reduced with negligible impact to a project. On the topic of embodied versus operational, here's an interesting extension of a slide we referenced earlier, which is used to shift the discussion towards embodied carbon over long-term operational carbon impacts. So if a building is being designed for a 10-year lifespan, you can see 74% of its impact is embodied. If a building is being designed for a 30-year lifespan, 49% of that impact is embodied. But if we extend the impact or the building to a typical 60-year lifespan, you can see that the impact then changes to about 20%, 26% being embodied, while the other 74% is operational. This slide is only to point out that arguably operational carbon can still be a significant carbon impact. And understandably, improvements to the grid will help this cause, but what I want to highlight is that structural system selection can also help it as well. And this is where concrete's thermal mass benefits can come into play. In a building, it is the mass of the structural elements that slowly absorbs and stores heat energy during the warmer periods of the day and slowly releases it during the cooler evening hours. Concrete is one of the few building materials that possesses this property, providing seasonal benefits to building operations. A concrete structure will aid in dampening the peak indoor temperature, in effect reducing the energy demand to maintain temperature when compared to alternate structural systems. And additionally, the energy absorption and desorption effects will shift the peak energy demand to later periods of the day where energy costs and needs are going to be lower. This also has the added benefit of allowing a designer to scale back equipment sizes and needs, proving beneficial to a project's budget. Actually. Here, I want to take a brief moment to highlight an academic analysis of various structural systems that involves looking at a cradle-to-gate impacts compared to cradle-to-grave impacts. The goal here is to emphasize the need to have a holistic view and analysis when making decisions on structural systems. This study was undertaken by MKA, leveraging Tally LCA software over a 60-year life cycle. So the 4 structural systems that were compared were as follows. Design A, blue lam beams and columns with nail laminated timber flooring, above grade with a concrete topping for acceptable vibration and acoustical performance, as well as mildly reinforced concrete slabs at level 1 and 2. Design B, steel beams and columns with 3-inch concrete slab over a 3-inch corrugated metal deck above grade with a 10-inch mild reinforced slab on level 1 with concrete columns below grade. Design C, an 8-inch post-tension concrete slabs above grade with a 10-inch mild concrete slab at level 1 and concrete columns. And lastly, design D, which is 10-inch mild reinforced concrete slabs and concrete columns. So initially, when looking at the cradle to gate scope of the study, the timber scheme, design A, appears to offer an improvement over the other systems regarding sustainability. This is largely due to some inherent biogenic carbon benefits that are captured in the early phase analysis of the material. As mentioned earlier, though, in the presentation, EPDs cannot be used to compare different materials, and this is one such case as the inputs for the EPD will vary. For instance, carbon absorption benefits and recyclability of concrete are not captured in this phase for the concrete materials. When transitioning to a full and holistic cradle-to-grave review of the various structural systems, we find a normalizing of their individual benefits and drawbacks, yielding a result where all structural systems are within a reasonable percentage of them. In this particular study, we find that the steel design B and the post-tension concrete design C can potentially be the most efficient sustainable systems, whereas the timber scheme design A is seen as increasing due to the end-of-life processing of the timber materials, in which a portion of that encapsulated carbon is eventually re-released into the atmosphere. Probably the most important thing to highlight here, though, is that this still isn't intended to be a direct comparison of structural systems, since this is just looking at the structural materials. What this does not include is operational benefits that may be captured with a concrete structure's thermal mass, as well as the fact that steel buildings make more frequent use of architectural finishing around columns and drop ceilings and things of that nature, which ultimately will have sustainability impacts. This highlights the importance ultimately of leveraging a true whole building life cycle analysis when making decisions, especially when sustainability is a goal of the project. To conclude here, the range shown in figure 9 and based on the previous discussions, that illustrates that making decision on a sustainability winner of sorts between the different alternate building systems with today's available LCA information is not always appropriate. The paper ultimately does affirm that designers should choose materials that are most materially efficient for the intended use of the building, and then to optimize and economize the design to save on quantities while also finding ways to decrease the embodied carbon of that material of choice. So at this point, I would like to hand it over to Don Davies, who's the president of MKA, to provide some real world insight into LCA of structures on his projects. Don?
Thank you, Brandon. And let me just get the right screen up here. And so you guys are looking at, make sure you see my screen with San Diego. So Brandon, thank you. I didn't know you were going to end with that prior study that we had done. There's one other punchline I'd like to put in that, and that we've certainly done in later studies, which is that where the material comes from is as big or bigger of an issue than the choice of the material. And it really further emphasizes this, hey, we need to go to EPDs and look at the information that comes from them. Because the choice of what forest it came from in the wood or what concrete batch plant and how optimized were their designs or not can swing those numbers significantly. That was certainly one of the findings that came out of that study. And is actually perfect lead into what I want to talk about here. This is the San Diego International Airport. I'm going to use it as a case study of how we talk about whole building LCA information, and how do we use this to make decisions. One of the things I'm seeing in the industry here is I don't think we're doing a good enough job educating our clients and on exactly what decisions we make for them when we step into a whole building LCA, or what information is telling us. So this is a case study of both findings of this project, but also just a little bit of a focus on how we talk about the information. One of the things we've started doing in our practice when we do step into LCA evaluations is the use of what I'm going to call a basis of analysis. And let's take the time up front let's write down exactly what it is we are doing. Just jumping to the punchline and showing, graphics of we saved you this much carbon on your building, but we haven't taken someone on a journey to explain how we've gotten there, what we've actually done. Many times there may be a lot of misinformation there, or, and frankly, missed opportunities to educate our clients. So spend the time, document something up front of what's, give a good project description. What units are we actually using? Super key here. Timeline, end of life assumptions. Brandon talked about that a little bit with concrete. We need to document these for our clients so they know what assumptions we are making for them. And frankly, don't make the assumption for them. Ask them the question. Make them be the decision maker on where we go with some of this. Also use it as a really good way to track and report the quantities over time. Any of this carbon modeling and carbon tracking, you can't manage what you don't measure. It all starts with the quantities. We need to know our quantities. We understand the uncertainty in the data and use that tracking forward. Certainly EPD reporting, it's simple math of carbon times quantities to come up with a GWP on a project. When you make it complicated, keep in mind that it's really that simple as the math we're doing. So as an example of this study, we do something up front that let's spend the time to explain to our clients what exactly is in or out of the building we are monitoring. Super important if it's a multi-phase project with multiple towers, but also explain to them if you're reporting carbon numbers, in this case, we're measuring the structure, the vertical, the horizontal, and the foundation framing. We haven't done the MEP systems as an example, or the facade system in this evaluation. Make sure they understand that. Many times you'd be surprised how much they really don't understand that in numbers of what we say. And an important topic for us to also get our arms around, if we're doing a whole building LCA, structure, skin, interior, services, contents, those all have a place in a true whole building LCA. So if we're only measuring the structure, one might argue that's not a whole building LCA, that's a structural LCA. We should be careful in our terminologies. Many times, especially if we're just measuring EPDs or reporting there, what we're really doing is tracking the upfront carbon, all the carbon that gets consumed in the structure. And I want to differentiate that compared to what I'm going to call whole building LCA monitoring. Upfront carbon is, say, if we were going to do structure, skin, interiors, we would measure all that gets consumed in order to build the building. But the lifespan of those materials are all very different. And so let's say we measure the contents. It may be a pretty small number in that carbon footprint of the upfront to build the building, but you're going to change those contents out every 10 years, whereas the structure maybe has a 100-year design life. Now let's compare that to if we were in, I think, true whole building LCA evaluations, where we're going to measure to a boundary condition. And let's say we take the 60-year boundary condition. If we're actually doing this right, we should, if the structure has a design life that's, say, longer than that 60 years, let's say it's a 100-year design life, we need to back that off to 60% of that total number. And then down there on those contents, we need to take the contents times 6 to be an apples to apples if we're measuring at the LCA boundary condition. It totally changes the dynamic of the numbers that we're talking about when we're explaining impacts to a client, but it brings a really important conversation to the table. Are we talking about, if we put a skin system in, do we put in a 20-year system, a 40-year system, a 60-year system? This is a way to resource level those. But we need to understand the implications of this ourselves, and then we need to better explain this topic to our clients. And frankly, they should be making the decision. Is it a 100-year structure? Is it a 50-year structure? Is it a 20-year skin? Is it a 50-year skin? They're going to be asking and making those decisions anyway, but when we talk about carbon, we should amortize that into the conversation so it's actually a fair and whole conversation. So in whole building LCA, I really advocate measuring at the boundary condition, but this time value of carbon needs to come into it. Another thing that we've been promoting is make sure we are talking the same units. I'm promoting all SI units and metrics just because we measure carbon in kilograms. So let's talk in square feet, or excuse me, in square meters per unit area divided by gross areas. But if you're making assumptions, if you're showing your information different ways, document that and communicate that so we know we're not comparing apples and oranges. And lastly, what we've been trying to do is I've created this table down below here where I'm showing all of those LCA stages A1 through C to D, but create a graphic that shows what are we actually measuring in the data we're reporting or not, and show what's a true measurement, what's a projected estimate, maybe what's industry average, or what we are not measuring. On this particular project, at the end of the day, we're going to measure the structure and the skin, and interior services and contents are not going to go into it. So when I'm reporting LCA data, I'm actually going to fill out this table to where the numbers actually show up. I can explain it as some graphical outputs, but as well as in the data table. So there's a good way to track the information as we go forward. And I encourage this color coding as a thought process of how we describe the quality of the data we're looking at. So on this project, and I'm not going to go into all the minutiae because of our interest of time, here's the bar charts of what we've seen. This project isn't built yet, but from our baseline to SD to DD, from our baseline building, we're showing about a 23% decrease that we've accomplished in the project. A lot of that has come through our system choices, but here, I'm not only showing the bar charts of the numbers, I'm also putting whisker bars on it. I'm showing the uncertainty in the data. Now, in this project, we're at DD. We don't know the vendor suppliers yet. And so we're really not moving past the industry average EPDs to vendor specific yet because we don't have that information. So my whisker bars are pretty large. We need to carry that information forward for our clients. And I'm going to move quickly through here, just a couple more topics before I hand it on. So what are some of the strategies we're doing in the building to reduce our carbon footprint? Especially, so we're talking about concrete here. As we said, know that concrete had the EPDs, Brandon talked about those, moving to the vendor-specific EPDs, that lets us get very tight on the uncertainty of the data, and there's true value when we go from the industry average to the vendor-specific and create that cost, ask for the EPDs at the time of procurement, so we can differentiate between double bottom line accounting cost and certainty. Brandon talked about the different variables that can go into what makes a mix. Pay attention to the aggregate supply. Know that quality control in the aggregate can be as big of a swing as the use of SCMs and how you get to lower carbon concrete. And especially different types of cement, which Brandon had also mentioned in blended mixes. But ultimately, as specifiers of our buildings, we don't really have to go too deep into how to make the concrete. In fact, the best thing we could do is stop trying to tell the experts in that topic how to do their job and ask them for what we really need and then challenge them on that. So what we have done, our specifications have gotten really simple. We simply just add 2 statements into the standard specification. We're going to ask for EPDs. You need to give us a type 3 vendor specific EPD for the material, not just concrete, for other materials. And then we're also going to ask our contractor to track, report the bill of materials on the project, and we want to track that through the design of the project. Don't make the specs overly complicated in this, keep it fairly simple, but make the ask. When we do make an ask for concrete, you want to do a performance-oriented specification. Ask for the information we really need. Give them the strength, but we are not asking, as an example, for a water cement ratio. Get the structural criteria we really need, and then say, meet these performance criteria. Give me your EPD that meets these performance criteria. I'm not going to tell you how much fly ash or slag to put in your mix. That's for you to figure out. I just want the EPD, and I'm going to track it that way. Just tracking and asking the questions, what we have seen in the 2 years that the EC3 tool has been in existence and we're asking for EPDs, we've seen almost a 20% reduction in markets that EPDs are actively being used by the ready-mix suppliers, and they know they're being compared. There's a lot of low-hanging fruit out there if we just simply ask for the data and then compare it. And this is for 5,000 PSI concrete. This happens to be the Seattle market, but we're doing the same thing in these asks in San Diego right now. The ready mixers suppliers start paying attention. They start figuring out how to optimize their mixes, and you start seeing these reductions over time. And this is coming, frankly, without a cost add. This is just by people paying attention to the data. That's real progress in our industry. Because we're talking about concrete and steel, quickly about steel, and then I'm going to stop. We want to ask for mill certs. They can get vendor specific mill certs at this point, especially in California. Steel is an internationally sourced material, but in the US especially, it's all about the electric arc furnace and the carbon footprint of electricity at the mill. That's what makes a difference on where the source of the material comes from. This is tracked through in an EPD. One last one I'll put out there that we found on this airport project. We have a lot of BRB, buckling restrained braces in the building. Those buckling restrained cores, if you don't ask the question, often would be coming from China and or Russia, first generation integrated mill delivery. Turned out, while that was only 10% of the steel material going into the project, it was 50% of the steel carbon footprint. Ask the question where the material comes from, domestic versus international electric arc furnace versus other EPD from that material. We can get a domestic sourcing that turned out of this material, and we've cut the carbon footprint of our BRBs by almost half at almost no cost add to the project. We want to ask those questions. We want to find that low-hanging fruit and then leave that to where that goes. And with that, I'm going to pass this on to Stacy to talk a little bit more from the architectural side.
Great, thanks, Don. Let me go ahead and see if I can steal the screen. Okay, you should be seeing my my screen right now. So, wow, I mean, so much really great technical information. You can see there's a lot of brain power in this room. I really appreciate all of this, and Don, especially, such a great way of distilling such complex information. What I want to do is I want to shift gears a little bit. I think when we think about trying to scale this conversation to a broader audience, it's really important that we normalize to designers, architects, and our clients who aren't going to be experts in this per se, right? How do we tell this story of how important this is so that they can embrace it and implement these strategies in their own projects? So I want to take a look at this project. I'm going to use the same case study that Don shared, but look at it from a slightly different perspective. So the San Diego International Airport is located in the northwest portion of downtown San Diego. It shares adjacencies with the San Diego Bay. There's a Navy boat channel down there. It's a dense urban mixed-use downtown district. If you're not familiar with San Diego, definitely recommend to get down there. It's really important, not only this project, so it's not only important to the environment, but also to the greater community of San Diego. There are a few specific environmental considerations that we had to be aware of. One is that there is an endangered species known as the least tern that actually nests and breeds on this airport campus. The other is that, well, there's lots of them, but the other big one to be aware of is that the San Diego County is classified as what's known as a non-attainment zone, meaning that the air quality already exceeds the national recommended limits for ozone. So environment is already a little bit of a concern. And then on the social impact perspective, San Diego is one of the top 20 vacation destinations in the US. And another fun fact for you is that it was actually the birthplace of California. So when the original Spanish settlers came to California, they took root there. So there's a lot of historical context in this community. And that's to say that this development had to be very special, very incredibly thoughtful in our application of all of the materials that we put into it. So the redevelopment project was centered around a 30-gate terminal, which replaces the existing 18-gate terminal. The other significant components of this project is that there were designs for significant accommodations to both airside, that's where the airplanes are, and landside, that's where the people are. There's a new roadway access from North Harbor Drive that's a component of this project. There is a new 5-level above ground parking plaza. There are upgrades to the central utility plant, as well as enhancements to the stormwater capture and reuse facility. And then this whole project was about future proofing for flexibility and resiliency. So there are infrastructure being built into this project to provide for future mass transit station, as well as other larger improvements. So huge impact to the community. You can see the lower left-hand corner is the existing site, and the big picture on the top is the proposal. So San Diego, when we approached this project, they already had a long-standing commitment to environmental stewardship. They were the second airport in the world to achieve a carbon neutral rating through what's called the Airport Carbon Accreditation Program. They received that in 2018. And what that includes is this third-party certification that's a verification of the carbon emissions associated with the entire campus. So it also requires that they have annual accounting of that carbon footprint, and that there are reductions that are designed for, and that at the end they offset their impact so that they can achieve carbon neutrality. They have a lot of other policies associated with any kind of development on the airport campus. I won't go into all of those, there are a lot. But as far as specific requirements to quantify the impact, we have the new terminals required to be designed and to achieve a LEED version 4 silver or higher. The parking plaza designed for Park Smart Gold, which is the companion program to LEED, but for parking plazas. And then the air side and land side, that's all infrastructure. That's a lot of concrete and cement, but also a lot of utilities and bridges, all of that good stuff. All of that is certified under a program called Envision. And they are required, their various scopes of work are also required to get a silver rating under those programs. And then the Airport Carbon Accreditation Program I mentioned, so they have to recertify every 2 to 3 years. So keeping that carbon footprint low for the entirety of the campus, that's really important to them. So all that's to say that there's a lot of eyes on this project, and a lot of sustainability that is the goal, right? When we look at something like concrete, right, and we think about, so not only from the owner's perspective, we have to end the alignment with their core values, and we think about all of the impact that's associated with those goals. You can imagine that this project requires a lot of concrete. If I say that in a different way, all of the infrastructure. So our total volume, our purchasing capacity is pretty high, right? So last year, in the US alone, 90 million metric tons of cement were produced to serve new build capacity, right? About a ton of concrete produces about 9/10 of a ton of CO2 emissions. So that's a good rule to live by. So in this case, last year alone, the total carbon footprint of concrete was the equivalent of burning about 1 billion pounds of coal in the United States. And then we don't just work in the United States though, right? Cement's used globally. So globally, there was about 4.4 billion metric tons of cement produced, and that's about 4 billion metric tons of CO2. So that's a lot. It's the equivalent of about running about 1,000 coal-fired power plants 24/7, just dedicated to the production of cement for a year. And to compensate for that damage, if we were to, we would need to plant about 65 billion trees, and we would like to water them. We'd have to protect them from all the things that happen to trees, right? We'd have to do that for 10 years. And that would just offset the cement footprint for the year. Last year we planted about 1.9 billion trees. And so you can see that the cement footprint is about 34 times greater than the carbon sinks that we're creating to offset them. And that's just cement. So we have a little bit of work to do. And the other thing that I wanted to highlight, again, to normalize this conversation, we always talk about CO2. What we don't talk about too much is the other greenhouse gas emissions that are associated with the making of cement. So right now, about 60% of the energy to make cement and concrete comes from the burning of coal, and another 10% comes from the burning of gas. So when we burn fossil fuels, what happens is that we create nitrogen dioxide, we call that NOx, and also sulfur dioxide, we call that SOx. And what happens with those gases go into the atmosphere, they combine with oxygen and they create particulate matter, particularly ultrafine particulate matter, which is really bad, actually. So these particles, we call them PM 2.5, they're so small, they easily penetrate into the lower respiratory system, so in our bodies, right? And then what happens is they create inflammation in our lungs, and then that sends plaque to our lungs, and then the plaque builds up, and then more inflammation happens, and you can kind of see where this is going. Studies have found that inflammation is incredibly important because it translates into increased instances of cardiovascular mortality. So that's not good. And then meanwhile, we've got the NOx and in the atmosphere, and it's combining with volatile organic compounds, and that's what creates smog. So that actually exacerbates the accumulation of PM 2.5, and you can see again where this is going. So there were some recent studies done through Harvard research that found that for every 10 micrograms of PM 2.5 that's in the community, there's a 9% increase in cardiovascular mortality. And recent studies have found that the volume of PM 2.5 associated with the manufacturing of concrete, well, it varies, right? It varies across the industry. It varies across the different operations associated with producing cement. But there's some good research papers out there if you're interested in start seeking them out. But some mills can generate up to 7,800 micrograms of PM 2.5. So you can see that making concrete has a substantial impact on the health of the community. And so this is really the health footprint of concrete. So we have to really understand the whole picture. We've got the environment, but then we also have to understand the health implications. And what's good though, right? Well, we know, I think, Brandon shared some great stats, and Katie as well on the total footprint of concrete and cement in the industry. We have about 7% of total greenhouse gas emissions coming from this product. And so if we think about that and we translate that into the community impact with the PM 2.5, we really have to find solutions for reducing the volume of cement, both locally, but also globally. And they've done a really great job at illustrating how to do that. And what I think is important to point out is that, we have to learn how to quantify the baseline, to reduce the design case, and how to optimize industry. And when we look at, our opportunity to make change happen, this happens, 70 to 90% of a project's potential to make an impact really happens in early design. So as architects and designers, we need to immediately approach every project with this thought process so that we can make change happen. And similar to the slide that Brandon showed, we also have some top 10 strategies. We think a lot of times, well, we can't do everything, but can we at least do some things? And I don't need to go through all of these. They really build off of the other sets of strategies that were shared. But looking at this from a design perspective, we know we need to reduce the total amount that we build in general with virgin materials. We know we need to understand what a business as usual design case is by measuring it. And then we need to benchmark our designs. We have to, once we benchmark it, we really understand what our footprint is. And this is, I think Don's example was great at understanding and being able to then optimize that solution. That's what we really need to focus on. And then the last one is really to advocate for improvements. The simple act of asking for EPDs has enormous impact on the local supply chain. So I think that's the end of my slides. I can stop sharing, and we wanted to open it up to Q&A so that we can really help you guys be ambassadors of this message.
Yeah, thank you, Stacy. That was great, and obviously appreciate the additional perspective coming from your expertise. Few questions here. There is a few things also within the chat that actually I kind of wanted to address as well that is not maybe widely available to the audience on the Q&A side of things. To kick it off, there was a comment or question or so about concrete's recyclability being more so termed a downcycling of things compared to timber being reused. And I just wanted to touch on the comment there, and Don, you may have to have an opportunity as well to comment on things you've seen within your projects in the past in terms of, I would say, concrete can also be, a repurposed material, right? It's not prone to rot or water damage, so the longevity of the material is going to be fairly similarly set in stone. And there's cases of, foundations and podiums, things of that nature, after the exterior skin and other, above structures removed, that those things are repurposed and reused. So there is an upcycling or repurposing opportunity with concrete, and that's always the best case. It plays back to Stacy's comment about use less, or don't build twice type of comment, right? Build it, make it last, and then when you get to a purpose or a time when you need to change the use, try to repurpose the material. And there's also such thing as carbonation, right? Concrete will absorb CO2 over time, and that is a chemical process that is permanently affixing the CO2 within the concrete. So a concrete building, say if it's demolished in the aggregate, that aggregate will expose new surface area that absorbs CO2 from the atmosphere. And ultimately, that's never going to degrade into methane or other greenhouse gases and release to the atmosphere. And repurposed wood products, there are cases where definitely they can be reused and upcycled of sorts, but then there's also going to be byproduct waste from that is going to go to landfills, break down, and CO2 would be released to the atmosphere. So it's a much more complex answer than just saying, getting more creative, I guess, is really the solution there, right? So Don, I don't know if you had any comments on that from your perspective.
I'll just add the comment that I really encourage everyone to go back and look at those slides where I was talking about whole building LCA, where we talk about the upfront versus the whole building at a timeline. It's how we can start to have the conversation to talk about durability and longevity of buildings and show to our clients the value proposition of repurposing and keeping a building. The upcycle, downcycle, I'd rather repurpose and re-renovate a building than tear down and build it new every time. And other than that, it's a bigger conversation. I would also say this, though, when we always get into the steel, the concrete to timber debate, I have never done a project yet that is not a hybrid system that has all materials in it. And even the building that I call in that study, like the Brandon was showing earlier, comparing different systems, that steel solution and the mass timber solution, they have the same amount of concrete in them, and both of them have concrete in them. So many of our conversations, to me, is not it's not a steel versus concrete versus timber. It's like none of these materials are going away. We need to use them all in an optimal way to where they best do their job. And concrete is very uniquely purposed in what it does. And there's very few places when we're using the material appropriately that there's another material that can do that job better.
Yeah, very well put. Stacy, I'm not sure if you have the same perspective in terms of reuse as well, or repurpose.
I think we also have an ability to bridge connections. So this San Diego project that we're working on, turns out we had two other very large projects occurring in the region at the same time. And one of our projects, this stadium, right? They needed so much concrete so quickly that we're able to leverage the other project's demolition to create to source aggregate locally, right? So the building was coming down, crushed it on site, ship it over to the other site. So that's, I mean, I don't know that it's maybe the exact definition of recycling, but it's definitely repurposing locally for the same purpose. So I would call it recycling. I think that that's one opportunity, especially given like the quantity of projects we're all working on all the time and the speed of delivery, that it's a great opportunity for architects to get together and help each other in the shared mission.
Yeah, I always preach, we need to be experts in all materials and all processes, because it's not just one solution fits all. There's going to be efficiencies at every level of design, from the early stages to actual execution in the field. So moving on here, there's other few questions here on the Q&A. A lot of them are very concrete related. So I'll try to answer some of these and get some of the other input as well. Really quick, how much are the thermal mass benefits reduced by cladding or covering of concrete in any form? Under my perspective, I want to say that it's only improved by additional insulation factors. We often talk about such things as like insulated concrete forms, which is concrete wedged between insulation. There's kind of an insulating effect, and then also, again, the thermal mass dampening effect. So I would think it's not necessarily reduced. The benefits would only be increased. Not sure if anyone else has any other comments on that. If not, moving forward.
I'll throw a quick one out there to challenge how we think about insulation and carbon. This was on a concrete project, but it was a project that had extensive balconies on it. And we looked very carefully at putting thermal breaks and putting a Halfin system in as a thermal break between the balcony and the structure on this building all the way around it to improve that thermal performance. But what we found, and think about this for your clients, it was going to be about a $2 million ad on this project to put the thermal breaks in between the balcony and the slabs. We found if we just extended the concrete out, let the concrete do what concrete does, but take that same amount of money for those thermal breaks and upgrade the cladding system, we could spend half the amount of money and get twice the energy performance in the building over 50 years. So my comment just there is try to look at the problem holistically. Don't get too honed in on just one element. Thermal mass absolutely is a big benefit. Precast on the outside of the building is a great way to play with precast, maybe on the south side of the building where you take advantage of thermal mass and reduce the weight on another side. But make sure you just look at the whole story.
Yeah, and there are cases too where I've crossed with consultants and products and things that actually run air ducts and things of that sort through concrete directly to allow for the heat, the energy transfer, right, as the air moves through the material itself. So there's a lot of creative solutions out there to look at holistically. Next up, do you have information on green benefits of 1L calcium sulfoaluminate cement? So there's two things going on there. I'm not sure if on the comment of 1L being type 1L cement, which is Portland limestone cement, which is a C595 blended cement. So that's a cement that's more or less coming to the industry, whether you want it or not type of thing. And as it's a plug and play solution and offers about a 10% reduction in the GWP of cement compared to the traditional cement that we use, particularly in California. So that's an immediate 10% reduction on most projects. And then it can still be used with all the other technologies we talked about before. Calcium sulfoaluminate cement, so CSA cement, is more often termed your repair material. It's a very fast setting, in many cases, material. And I don't off the top of my head know the exact factors. I do know it is a greener material, but the setting characteristics and usage of it, it's not as widely available on a mass scale for, say, doing slabs, things of that nature. Might be something that could be explored for smaller elements like columns and things like that. But I will say that the future benefit of greener cements being, again, blended products, as well as there are very innovative things out there. Someone asked about the net zero goal of the cement industry, and that includes carbon capture, things of that nature, as well as the cement process changing chemically how you're actually handling the cement process to to reduce or remove the opportunity for CO2 to be released. So that's a whole other discussion. Reach out to me if you want to go into the weeds on that one. Moving forward.
Brandon, I think we're at time.
Oh, we're at time. Okay, so we'll try to answer as much as we can after this. Rebecca can distribute to the audience then thereafter.
Yep, definitely. I'll go ahead and send over the questions for you all to answer, and I'll put it in the follow-up email. And I just wanted to thank all of you again for this very informative presentation and for giving us your time. To the attendees who've made it this far, we will submit you for credit, and it will appear in your transcripts in a few weeks. And a recording of this presentation and additional resources will be posted soon. More information, like I mentioned, will be available in a follow-up email soon. And just a big thank you to everyone again. We'll see you on our next webinar.
Yeah, thanks.
Thank you, everyone.
Thank you.
Thanks.